Swayam Prabha. Digital India. Educated India.
The next important property of Fourier transform is like this. If the Fourier transform of the signal xt is capital X of omega, then the Fourier transform of x dot t, that is the time derivative of x, will be j omega multiplied with capital X of omega. Okay, let us prove it. Suppose the Fourier transform of x dot is equal to capital X prime. We do not know what is capital X prime, but we can definitely say that if this is the Fourier transform of x dot, then x dot is equal to 1 over 2 pi integration of x prime e to the power j omega t d omega. Omega from minus infinity to plus infinity. Let me call it equation 1. And then also, since capital X is the Fourier transform of small x, we can write that small x is equal to 1 over 2 pi integration capital X omega e to the power j omega t d omega, omega running from minus infinity to plus infinity. Now, in this equation, let us differentiate both the sides with respect to time. Then the left side will become dx dt and the right side will be 1 over 2 pi time derivative of this entire thing, which is integration of x omega e to the power j omega t d omega, omega running from minus infinity to plus infinity. Now this is equal to 1 over 2 pi, and let us swap the order of integration and differentiation, and this will become integration over omega from minus infinity to infinity preceded by the time derivative of capital X omega e to the power j omega t d omega. Okay, now this is same as 1 over 2 pi integration over omega from minus infinity to plus infinity. Time derivative of capital X omega is x omega itself, as this part does not depend on time at all, and time derivative of e to the power j omega t is e to the power j omega t multiplied with j omega. D omega is as it is. Now the trick here is to put a bracket and we are done. So here this is x dot t, and now you compare this equation of x dot with this equation of x dot. Okay, if you call this equation number 2, comparing equation 1 and 2, look at the right hand side, everything is similar. So x prime here must be equal to this term inside the bracket. So we have x prime omega is this thing inside the bracket, which is j omega x of omega, and that is the proof. Now the reverse, that is x omega is equal to x prime omega divided by j omega is also true provided if omega is not equal to 0. Otherwise dividing by 0 is undefined. In fact, you can notice from here one interesting fact that x prime of 0 is equal to 0 always for any signal xt. Okay, the derivative, the Fourier transform of the derivative will be such that its value is equal to 0 at omega equal to 0. And then you cannot get the value of capital X0 by this rule because 0 by 0 is undefined. Next, we shall look at time shifting property of Fourier transform. Once again, we start with the fact that Fourier transform of small xt is equal to capital X omega. Then let us consider a time shifted version of small x as say x of t minus t naught time shifted. Then what will be the Fourier transform of this signal? Let us find this out. Okay, the Fourier transform of x t minus t naught is by definition equal to integration of x t minus t naught e to the power minus j omega t dt, t running from minus infinity to plus infinity. Now, if you substitute t minus t naught with say tau, that means dt will be equal to d tau, and the limits it was t from minus infinity to plus infinity will become tau from minus infinity to plus infinity. Then you can write this as integration over tau from minus infinity to plus infinity x of this is tau, and then e to the power minus j omega t is equal to tau plus t naught, tau plus t naught, and d tau here. Then this will be equal to integration over tau from minus infinity to plus infinity x of tau. Let me break this tau plus t naught as e to the power minus j omega tau multiplied with e to the power minus j omega t naught, and then d tau as it is. Now notice this term is not a function of tau, therefore we will write it outside, okay, like this, because it does not depend on tau. Then we are done. So this is equal to e to the power minus j omega t naught, and this integration is nothing but by definition capital X of omega. So this is the answer. Let me put it here. It is e to the power minus j omega t naught multiplied with x of omega. Next, property is called modulation property. Once again, we start from Fourier transform of xt is capital X of omega. Now, if we multiply this xt with say e to the power j omega naught t, which is a periodic complex exponential function with a fixed frequency omega naught. Such multiplication of an arbitrary signal xt with such a periodic signal is called modulation of xt. And now the question is, what will be the Fourier transform of this product? Let us find it out. Fourier transform of e to the power j omega naught t x of t is by definition integration of e to the power j omega naught t xt dt, t running from minus infinity to plus infinity. Here we also have e to the power minus j omega t. Okay, now this is equal to integration of t from minus infinity to plus infinity x of omega, and let us merge these two exponential terms together as e to the power j minus j omega minus omega naught t, like this, and dt, and we are done. So this is nothing but, you can recognize this is equal to capital X of omega minus omega naught, because capital X is the Fourier transform of small x. So that means capital X is integration of xt e to the power minus j omega t dt from minus infinity to plus infinity. Now here if you put in place of omega, omega minus omega naught, then here also you have to put in place of omega, omega minus omega naught, and then that is exactly what we have here. So this is capital X omega minus omega naught, and this is the answer. So let me put it here. It is capital X omega minus omega naught, as if this capital X, this function is shifted in the omega domain by an amount of omega naught towards the right. Okay, and therefore this property is also called frequency shifting. So when you multiply e to the power j omega naught t with a signal, then the Fourier transform gets shifted by the amount omega naught. On the other hand, we saw previously that if you shift the original signal xt by an amount t naught, then the Fourier transform becomes the Fourier transform of this x, capital X, multiplied with e to the power j omega t naught. So in a sense, this property and this next property are like mirror image of each other. That is easy to remember. Now, before proceeding further, you have a homework. If the Fourier transform of small x is capital X, then what will be the Fourier transform of the product of small x and sine omega naught t, or small x multiplied with cosine omega naught t. To find this, you can write this sine or cosine as a sum of two exponential signals and then use this previous property, that is the modulation property. Do it now. Now this is probably the most important property, that is the convolution property, which says the Fourier transform of x star y, that is the convolution between x and y, is equal to capital X of omega multiplied with capital Y of omega, where clearly capital X of omega is the Fourier transform of small xt and capital Y of omega is the Fourier transform of small yt. That means the Fourier transform of the convolution of two signals is equal to the product or multiplication of individual Fourier transforms. Let us prove this property. Okay, so let us start from the Fourier transform of x star y. This is by definition x star y multiplied with e to the power minus j omega t integrated from time minus infinity to plus infinity. Now this is equal to integration over t from minus infinity to plus infinity. Here e to the power minus j omega t dt, and inside the bracket here let me write the expression of x star y, that is x tau y t minus tau integrated over tau equal to minus infinity to plus infinity d tau. That is the formula for convolution. Now let us manipulate this. Here t equal to minus infinity to plus infinity, and then tau equals minus infinity to plus infinity, x tau y t minus tau this d tau, and let me put this e to the power minus j omega t inside the first inner integration, because this part does not depend on tau, so it is like a constant, so we will put it inside the inner integration, and this dt as it is. Now we have a double integration, so we will swap the order of integration this way. First tau from minus infinity to plus infinity, then t from minus infinity to plus infinity. Here we have x tau y t minus tau e to the power minus j omega t. I will write dt first and then d tau. Now you notice that this x tau is not a function of t, so I will write it outside here and like this. So the inner integration is over t and the outer integration is over tau. Then I will apply a substitution. I will put this t minus tau equal to say p. So which implies that dt is equal to dp, and the limit of the inner integration, which was t equal to minus infinity to plus infinity, will become p equal to minus infinity to plus infinity. So this is equal to x of tau as it is, and here this will be integration over p equal to minus infinity to plus infinity y. This will become t, and e to the power minus j omega. In place of t, I will put tau plus p in this way, tau and then e to the power minus j omega p. Then dt is dp and d tau as it is. Now you observe that this e to the power minus j omega tau does not depend on p. So I will bring it outside here, and let me write these terms closer. Also, this d tau can be written here, okay, with the first term, like this, and we are done. Now you see this first term here is by definition capital X of omega, Fourier transform of small x, and the second term is the Fourier transform of y, capital Y of omega. So that is the proof. Now you should notice that in all these proofs, the bag of tricks, or my bag of tricks, is not a huge one. I am applying the same type of tricks again and again. And I also suggest you not to memorize these formulas. Rather, whenever required, try to derive these formulas, because it will not take much time. If you try to memorize blindly, you may make mistake. Rather, spend 1 minute, derive the formula, and then use it. Next, we shall calculate the Fourier transform of some standard, well-known simple functions. For example, delta t. What is the Fourier transform of unit impulse function? It is very easy. You should try it yourself. Fourier transform of delta t is by definition integration of delta t e to the power minus j omega t dt, t running from minus infinity to plus infinity, and this integration with this delta function, you know, is equal to e to the power minus j omega t, this function evaluated at t equal to 0, which is 1, and that is the answer. Very important result to remember. Next, consider a signal, very simple signal, xt equal to 1 for all time, constant, from minus infinity to plus infinity, all time, this is equal to 1. Okay? So what will be the Fourier transform of this signal? That is, what is the Fourier transform of 1? This is a bit tricky, at least if you want to use the direct formula. At first it will be difficult. Let me give you a simple trick. Okay, I will use the inverse formula. So suppose the Fourier transform of 1 is equal to say capital X of omega. Now that means 1 is equal to capital X omega e to the power j omega t integrated over omega from minus infinity to plus infinity, and then 1 over 2 pi, which means that this right hand side integration of x omega e to the power j omega t d omega over all omega, this is equal to 2 pi. Now try to guess, do you know any function which if you put in place of capital X omega and do this integration, it will give 2 pi? The answer is x omega is equal to 2 pi delta omega, because if you put here 2 pi delta omega and then this e to the power j omega t d omega integrated from omega equal to minus infinity to plus infinity, then this integration is easy to evaluate. This is 2 pi, this constant, and then the remaining term will give you e to the power j omega 0, which is 1. That is 2 pi only. Okay, so this is a kind of back calculation which tells that the Fourier transform of 1 is this. Let me write it here, 2 pi delta omega. We have found this using back calculation in this way. Next, we shall learn duality property. We know that the Fourier transform of any signal small x, which we write as capital X of omega, is given by the integration xt e to the power minus j omega t dt from t equal to minus infinity to plus infinity. And you can get back this small xt using the inverse formula, which is integration of capital X omega e to the power plus j omega t d omega, omega running from minus infinity to plus infinity, and here 1 over 2 pi. This is called the inverse Fourier transform, which we may write as f inverse x omega. Notice a nice similarity between these two formulas, except that here t is the variable and here omega is the variable. Here we have a minus sign, here plus sign, and here there is a 1 over 2 pi which is absent here. Otherwise there is some similarity between these two formulas. Using this similarity we will derive our duality property. For that, let me first ask one question. Suppose we have a function x of t. The Fourier transform of this function is capital X of omega. Now this small x is a function whose variable is t, but I can also write this as x dot without mentioning what is the variable. Okay, so this x may be something like sine, cosine, log, exponential, polynomial, but I am not mentioning the independent variable. Similarly, this capital X is also a function by itself, even if I do not mention what is the variable. I will just put a dot. Dot means I am not telling you what is the variable. We know the variable here in this case is omega, but consider x just as a function, sine or cosine or something, without telling what is the independent variable. Now, between small x and capital X, the connection is that this capital X is the Fourier transform of this small x. Okay? Now I am asking, if you consider this capital X as a function, then what will be the Fourier transform of this capital X? Of course, I mean, to make this question more meaningful to you, I may ask, what is the Fourier transform of capital XT? Okay, so I am asking, suppose for some small x, the Fourier transform is, say, sine omega. Okay, for some signal. Then I am asking here, what is the Fourier transform of sine t? That means I am changing the variable omega here with t. So for some x, if sine omega is the Fourier transform, then my question is, what is the Fourier transform of sine t? To make my question a bit more clear, let me give an example. I mean, we have seen just now that the Fourier transform of 1 is 2 pi delta omega. We have proved it few minutes back. Now this 2 pi delta is a function. Okay, so 2 pi delta, you consider it just as a function without regarding this omega as the variable, and I am asking, what is the Fourier transform of this signal? What is the Fourier transform of delta signal? That is my question, for example. Of course, to make it more meaningful, you may think that here in place of omega, I am thinking of t, and then asking what is the Fourier transform of delta t. And we also have seen this few minutes back. This is 1 multiplied by 2 pi, because Fourier transform of delta is 1. So the question is, if Fourier transform of 1 is delta, then what is the Fourier transform of delta? Okay, so that is the question. And also from this example, you might have guessed that if Fourier transform of 1 is delta, then the Fourier transform of delta is 1, disregarding these constants for now. So we will also see that if the Fourier transform of small x is capital X, then the Fourier transform of capital X will somehow be given by small x. That we shall see now. Okay, let us begin from, say, this equation. Let me call it equation 1 and equation 2. Now, from equation 2, okay, we have small x t equal to 1 over 2 pi integration capital X omega e to the power plus here plus j omega t d omega, omega running from minus infinity to plus infinity. Now please observe that in forward and inverse Fourier transform, the role of these two variables t and omega is swapped or interchanged. Keeping that in mind, here in this equation I shall try to swap the names of these two variables t and omega. For that, let me copy this equation and let me replace this variable t both in left and right side with a new variable. Call it p. Then let me copy this equation again. And now I shall change the name of omega. Okay, anyway omega is a dummy variable which will disappear after this integration is over. So I can easily change it with a new variable. Let me call it t. And then copy this equation again, and now I shall replace the variable p both in left and right side with a new variable, and I will call it omega. Now through these three steps I have actually swapped or interchanged the role of t and omega completely. Here t becomes omega here, t becomes omega here, and omega here, here and here become t here, here and here. Now the right side in this equation is nothing but Fourier transform of this signal capital X of t. However, this is at frequency minus omega, because you know that Fourier transform of capital XT is by definition capital XT multiplied with e to the power minus j omega t integrated from time t equal to minus infinity to plus infinity. And this is the Fourier transform which is a function of omega, so I can put omega in this way. Okay, and now if you put minus omega in place of omega in the left side, you have to also put minus here, which will make it plus. Okay, and this is exactly what we have here. I missed this constant uh, let me write this constant 1 over 2 pi. Okay, so from here you can write that Fourier transform of capital X of t as a function of minus omega is equal to small x of omega multiplied with 2 pi. And now if you want to get the Fourier transform of capital Xt as a function of omega, you have to put minus here, that means also a minus here, so that will become x, small x of minus omega multiplied with 2 pi. Okay, and that is the answer. Okay, so here the answer will be the Fourier transform of capital X is 2 pi into small x minus omega. To make it more clear with an example. So we know that Fourier transform of delta t is 1. Therefore, if you want to calculate Fourier transform of 1, according to this formula, we should get this 2 pi and then this delta with minus omega as the argument. However, delta is an even function, therefore delta minus omega is same as delta plus omega. So that means according to this formula, Fourier transform of 1 should be 2 pi delta omega. And indeed it is. Just few minutes back we have shown that Fourier transform of 1 is actually 2 pi delta omega. Okay, so this formula, this rule which we call the duality property of Fourier transform is giving correctly the Fourier transform of 1 which is 2 pi delta omega. So according to this duality property, if the Fourier transform of small x t is capital X omega, then the Fourier transform of capital X t is equal to 2 pi small x minus omega. Next, let us learn another new property. Suppose the Fourier transform of small xt is again capital X omega, then what will be the Fourier transform of t multiplied with xt? That is the question, and let us find it out in this way. We know that capital X omega is equal to small x t e to the power minus j omega t integrated over time from minus infinity to plus infinity. Now let us differentiate this equation both the sides with respect to omega. So the left side will become dx d omega and the right side will become integration from minus infinity to plus infinity. Now we have to differentiate these terms with respect to omega, but small xt is not a function of omega, so that we can keep as it is like a constant. And if you differentiate e to the power minus j omega t with respect to omega, you will get e to the power minus j omega t multiplied with minus j t and this dt here. So this is equal to integration from minus infinity to plus infinity, and here I will write this as t followed by xt followed by e to the power minus j omega t dt, and this minus j I will put outside here. Now you notice that if I just put a bracket across t and xt, then this integration looks like the Fourier transform of txt. Okay, so then the right side is minus j constant, and then Fourier transform of txt. So from this we can write the Fourier transform of this txt is equal to dx d omega, d capital X d omega, and then divide by minus j, so that will become plus j. So this is the answer. So let us put the answer here. It is j dx omega by d omega. Okay, next suppose we have a signal x of t which is defined as sine Sij and sine of t. So that means it is equal to plus 1 if time is greater than 0, and this is equal to minus 1 if time is less than 0. So if I plot this signal as a function of time, then sine of t, this is also called signum t, that will look like this: minus 1 here and plus 1 here, plus 1 minus 1. Now the question is, what is the Fourier transform of sine t, Sign t? Let me find this answer in the following way. Let me first draw the signal which is time derivative of signum t. Now as you know that the derivative will be 0 almost everywhere, except at the origin where we have a finite jump. Okay, and the amount of jump is from minus 1 to plus 1, that is 2. So here we will have to put a delta signal, impulse signal, with an amplitude of 2 delta t. So this is the derivative of signum t. You know that Fourier transform of a signal, for example signum t, is equal to the Fourier transform of its derivative, that is d dt of signum t divided by j omega. This is true except at the point omega equal to 0. Now this d dt of signum t is 2 delta t, so this we will write as Fourier transform of 2 delta t whole divided by j omega, and we have calculated that the Fourier transform of delta t is 1, so this will be equal to 2, and the Fourier transform of delta is 1, so divided by j omega. This is of course true except at omega equal to 0, and at omega equal to 0, let us calculate that separately. When for omega equal to 0, the Fourier transform of signum t at omega equal to 0 is by definition signum t multiplied with e to the power minus j omega t dt integrated from time minus infinity to plus infinity, and here we have omega equal to 0, so e to the power 0 is 1, so we have basically signum t integrated from minus infinity to plus infinity, and by virtue of the symmetry or antisymmetry of this function, this integration will be 0 because this is a odd function. Okay, so finally my answer becomes the Fourier transform of signum t is 2 over j omega if omega not equal to 0, and this is equal to 0 at omega equal to 0. Next, what is the Fourier transform of ut, unit step function? This is very easy to find out at this point. Ut can be written as signum t plus 1 whole divided by 2, because here you see this is how signum t looks like. So if you add 1, a constant 1, that means 1 for all time, if you add that, then before t equal to 0, plus 1 minus 1 will cancel and will become 0, and after t equal to 0, 1 plus 1 will be 2, and therefore that signal will look like this. It will be 0 here and then go up and constant 2 like this. Okay, and if you then divide that with 2, you will get unit step signal. Okay, now if this is the case, and also another fact that Fourier transform of say sum of two signals x1t plus x2t, okay, this is always equal to the Fourier transform of x1 plus the Fourier transform of x2. Fourier transform is linear in nature. it obeys homogeneity, superposition, etc. I mean, this is very easy to prove. That is your homework. Okay, and if so, then the Fourier transform of ut can be written as the Fourier transform of this thing, sine t plus 1 whole divided by 2, and that will be equal to this half common, and Fourier transform of sine t and Fourier transform of 1 are to be added. Now Fourier transform of sine t is 2 by j omega, we calculated just now, and Fourier transform of 1 is 2 pi delta omega. We calculated it today only. So this becomes, this 2 goes away. We have 1 over j omega plus pi delta omega. So that is the answer. A very nice and important result for us. Next, we shall talk about the integration property. Suppose that the Fourier transform of a signal xt is equal to capital X of omega, and now let us consider the integration of x like this, x tau d tau integrated from tau equal to minus infinity to time t. You can call this a new signal yt. So if x is a signal like this as a function of time, then this integration gives us the area under this curve starting from minus infinity up to a particular time instant, call it t, and this area is y of t, which also changes as time increases. Now for this integration to be well defined, we should better have the value of xt at t tending to minus infinity equal to 0. It is better that the signal x dies down to 0 when time approaches minus infinity, because otherwise when you integrate the area starting from minus infinity, you will get an unbounded, undefined value. So for this integration to be properly defined, we should better have the value of x at minus infinity equal to 0. Now, if the Fourier transform of x is capital X and y is the integration of small x, then the question is, what is the Fourier transform of y? That is, what is the Fourier transform of integration of x from minus infinity to t? That is the question. And we can find the answer very easily. If you recall that this y, which is the integration of x tau d tau from minus infinity to t can be written as the convolution of x with unit step function u. This is something that we have seen in our first week of this course. Okay, so you should be familiar with this idea that integration of x from minus infinity to t is same as the convolution of x with unit step function. And today we have learned that the Fourier transform of the product of say two signals x1 and x2, sorry, the convolution of x1 and x2 is given as the Fourier transform of x1 multiplied with the Fourier transform of x2. If that is the case, then here Fourier transform of y is basically the Fourier transform of x convolved with u unit step, which is same as the Fourier transform of x multiplied with the Fourier transform of u. Fourier transform of x is capital X. It is given in the question. And Fourier transform of unit step function is what we have calculated just now. It is pi delta omega plus 1 over j omega. Okay, this is from here. Now you may simplify this a bit. This is equal to x omega pi then delta omega plus x omega by j omega, and now the first term is pi, and then this x omega delta omega, you know this is same as x0 delta omega plus the second term as it is x omega by j omega, and that is a very important result for us. Next, some simple properties or results that we can actually get by using the previous properties, but these properties are also very important. For example, what is the Fourier transform of e to the power j omega naught t? This is a function of time t. Omega naught is a constant. So we have a periodic complex exponential signal whose Fourier transform is to be calculated. This is easy to do. For this, we will use the property. Let me go back. Here, the modulation property. Fourier transform of any signal multiplied with e to the power j omega naught t is equal to capital X omega minus omega naught. So here this is like the Fourier transform of e to the power j omega naught t multiplied with 1, and the Fourier transform of 1 is 2 pi delta omega. Now because of this e to the power j omega naught t being multiplied, here we have to replace omega with omega minus omega naught. That is the modulation property. Okay, so that is the answer. Next, suppose we want the Fourier transform of sine omega naught t. That will be same as the Fourier transform of e to the power j omega naught t minus e to the power minus j omega naught t whole divided by 2j, and then it will be equal to 1 over 2j common. Then we have to add the Fourier transform of e to the power plus j omega naught t and Fourier transform of this other term e to the power minus j omega naught t. So that will be like this. The first term will give us from here 2 pi delta omega minus omega naught, and the second term will give us this minus, and it will be 2 pi delta omega minus minus omega naught. This is because here this you may write as j and then minus omega and then minus and then t. Okay, so this term is exactly similar to this term, except omega naught is replaced with minus omega naught. So here in place of omega naught, if you put minus omega naught, that will be the Fourier transform of this part. So this is equal to these 2's will go away, and we have pi by j, here delta omega minus omega naught minus delta omega plus omega naught. Okay. Next, in the same way, you can calculate the Fourier transform of cosine omega naught t. That is same as the Fourier transform of e to the power j omega naught t plus e to the power j minus omega naught t whole divided by 2. So that will be equal to half. Then this will be 2 pi delta omega minus omega naught plus 2 pi delta omega plus omega naught. Okay, which is same as pi delta omega minus omega naught plus pi is common, so plus delta omega plus omega naught. Now I shall finish today after drawing these few functions as a function of omega. Okay, so let me draw this Fourier transform of e to the power j omega naught t as a function of omega. That is the spectrum of e to the power j omega naught t. So that is this 2 pi delta omega minus omega naught. Now this is a delta function and located at omega equal to omega naught. So assuming omega naught to be positive, say somewhere here, this is the point omega naught. Then here we will have a spike delta function like this with height 2 pi. So this is 2 pi delta omega minus omega naught. That is how the spectrum of e to the power j omega naught t looks like. Similarly, coming to sine omega naught t, let us draw the spectrum. Let this be the omega axis, and okay, here this is a complex number, rather actually imaginary number. So what I will do, I will plot the imaginary part of this Fourier transform. Imaginary part of Fourier transform of sine omega naught t, because the real part is 0 anyway. Real part is not there. Okay, and this you may also write in this way, minus j pi delta omega minus omega naught minus delta omega plus omega naught. Okay, so we will have two delta functions, one located at omega naught somewhere here, another located at minus omega naught somewhere here, and the amplitude of this delta function is minus pi. Okay, so here I will draw a negative delta function minus pi delta omega minus omega naught located at omega equal to omega naught. Recall, this is only the imaginary part of the Fourier transform, because I cannot draw both real and imaginary part together. Okay, and this delta function will be located here, and its amplitude is plus pi. So here another spike with height plus pi. This is pi delta omega plus omega naught. Okay, so this is the spectrum or the imaginary part of the spectrum of sine omega naught t. And previously we have seen that the imaginary part of spectrum or Fourier transform of any real signal must be odd in nature, and that is we also see in this example. Next, the spectrum of cosine omega naught t as a function of omega. So I am going to plot the Fourier transform of cosine omega naught t. Again we have two delta functions, one at omega equal to omega naught, another at omega equal to minus omega naught. Both of them have amplitude pi. So one spike here, which is pi delta omega minus omega naught, another spike here, which is pi delta omega plus omega naught. And this is actually the real part of this Fourier transform, because imaginary part is 0. And previously we have learned that the real part of Fourier transform of any real signal must be even. And yes, here also in this example, this Fourier transform is an even function. That's it for today. I request all of you that in your weekend You practice all these properties again and again. Do not try to memorize them. Practice the derivation. You will automatically remember them. Utilize your weekend and enjoy your weekend.